today I will be presenting on my findings from Lab 2. In my presentation, I will have 3 sections. The first is an introduction, where I will discuss the purpose of the lab, the fundamental principles involved, and a summary of my results. Second, I will be discussing my data, measurements, and observations in both the physical experiments and in my glow script model by comparing and contrasting my results from Lab 1 and Lab 2. Finally, I will be concluding my presentation with answers to a few thought-provoking questions. The purpose of this lab is to utilize the data from Lab 1 to model and explore the differences between point and line charges. This is important because it showcases more accurate ways to mathematically model charges, which can give us a more accurate understanding of our universe as we use those principles to model the phenomena that surround us. The fundamental principles showcased in this lab is Newton's first law and Coulomb's law. Newton's first law states that an object in motion stays in motion and an object at rest stays at rest unless a net force acts upon it. Coulomb's law states that the electric force magnitude and direction are governed by the relative size and sign, either positive or negative, of the two involved charges, respectively, and the magnitude is proportional to the inverse square of the distance between the charges. This means that, like the gravitational force, when the two charged objects are close by, the electric force plays a huge role in their interactions. However, when the electric force is far away, it plays a very small role in the interactions between the objects. Finally, the superposition principle states that the component vectors can be added to create a net vector. This is applicable in calculating gravitational and electric forces and fields. Throughout this lab, I have found that using a line charge model to calculate forces on a piece of tape is significantly more accurate than modeling the tape as a giant point charge. Before we jump into Lab 2, let's take a minute to review Lab 1. In my floating tape experiment, I used Newton's first law to create a free body diagram, treating the piece of tape as a point mass and point charge, seen here. I used this to calculate the magnitudes of the equal and opposite gravitational and electric forces and used these values to computationally determine the net charge on the tape while treating it as a point charge. However, in using the line charge visual model, it is clear that the point charge calculation from Lab 1 on the left is inaccurate to represent the total charge on the line charge, because the electrical and gravitational forces do not cancel out, implying that the tape cannot be at rest. In order to establish a zero net force with the line chart model, I had to approximate the net charge on the tape via the guess and check method. Because the net force is basically zero on the right, this is a significantly more accurate value for the charge on the tape. In order to properly code this model, I made 2 key assumptions. First, I ignored air resistance on the tapes. Second, I assumed that each U-tape had the same charge that was evenly distributed throughout, which allowed me to represent the tapes as infinitesimal equivalent point charges in my model. I made a number of alterations to the starter code to create my final model. First, I added the specific data relating to my piece of tape. This includes my estimated charge value that I discussed previously. Second, I created a calculation method for the electric field at any location using the typical R-vector calculation steps that we had defined in class. The following block of code defines how to calculate and display line charges using infinitesimal particles. I then created my top tape in red and my bottom tape in blue, using the 10 infinitesimal particles and altering the axis to set my bottom tape at y = 0 and my top tape to my measured levitation distance from the experiment. I then altered the various scale factors, and ran a nested for loop to calculate the net E fields and forces on each infinitesimal charge. A key line in this nested loop is line 130, where I applied the concept that F electric equals Q times E to each infinitesimal point charge. I finally created the net gravitational and electric forces to complete the model. After running my code, I got visual confirmation that I coded it correctly because the net forces are approximately equal, implying that both tapes, specifically the top tape, are in fact in rest, and each of the infinitesimal point charges has an approximately equal infinitesimal repulsive electric force shown in green. Before I conclude, I would like to address two key questions. First, if the tape had been modeled as a point charge, as it had been in Lab 1, the calculated charge would be significantly less than the calculated charge had it been modeled as a line charge. Specifically, my calculated charge for the value for the line charge model is bigger than my point charge calculation by 101%. Second, these charge estimates differ because the point charge model only considers forces in the y direction, while the line charge model accounts for forces of the bottom tape on the top tape in both the x and y directions. Because this method uses the superposition principle, it is closer to the real value. Thank you for watching, and I look forward to discussing more physics content during Lab 3.